Hello everyone. We were in module number 4 of computer communication network and we were discussing about network layer protocols. In the previous video, I have started with IPv4 datagram format and the different fields involved in it. So we have seen what are all the different fields we had and what is the size of that each of this bit and what is the purpose of each of this field in IPv4 datagram. Now let us move on to the next part of this, which is called as fragmentation. Fragmentation is nothing but dividing the datagram into number of payloads and transferring it to the destination. We have seen that datagram will travel through different network. So whenever the data moves, the each router which encounters this datagram, it will decapsulate the IP datagram from the frame whichever it has been received. It will be processed and encapsulate it again and send it to the next router or the destination. So depending upon the protocol used by the physical layer network, the format and size of the frame varies. For example, if you consider a network when it consists of different topologies like LAN, WAN, etc. If a router is used to connect a LAN and a WAN in a given network, then the router receives a frame in the LAN format. So since the data has coming from the LAN network, so the packet will be received in the LAN format and that router is linked to a WAN. So the data has to be or the frame has to be sent in WAN format. So based on the requirement, based on the requirement, the frame has to be sent as per the requirement. Let us move on to a topic called maximum transfer unit, nothing but the maximum size of a datagram that is required to transfer the data. As we know, each of the layer in a particular protocol has its own frame format. So the physical layer has one, the data link layer will have one, the network layer will have one. So each of the layer have a different protocols and each of this will have a different frame format. One of the feature of each format is the maximum size of the payload that can be encapsulated. So depending upon the protocol, the maximum size of a payload can be encapsulated. So the feature is that format is the maximum size of the payload that can be encapsulated. So that is the feature of each of the protocol in the particular layer. When a datagram is encapsulated in a frame, the total size of the frame should be or must be less than the maximum size. So there is a maximum limitation or for the size. So it should be always less than the maximum size specified. So which is defined by the restriction imposed by the hardware and software used in the network. So based on the hardware and the software specification, we need to restrict the size of a datagram. So the value of this MTU, that is maximum transfer unit, differ from one physical network protocol to one more physical network. For example, as I said in the previous case, LAN will have different MTU compared to WAN. So usually the value of LAN is usually 1500 byte. So that is the actual size of MTU. Whereas in case of WAN, it is larger than that. So you can see here in this diagram, so you have a payload. So you can see maximum size of a frame payload. So this will vary based on the protocol. You can see hyper channel, it is 65,535 is the MTU. When you take token ring of 16 Mbps speed, then it is 17,915. If token ring of 4 Mbps, then the MTU will be 4,464. If it is FTDI protocol, then it is 4,352. If you are using Ethernet protocol, then the MTU will be 1,500, and if it is x.25, then it is 576, and if it is a PPP protocol, then MTU will be 296 bytes. So what are the values mentioned here? All these values are in terms of bytes. So depending upon the protocol, depending upon the different protocol, the size of the payload will vary. So this is a reference where for the different protocol the MTU has been specified here. In order to avoid these kind of issues, or to make a protocol independent of physical network, uh, now the designers are, or they have a restriction, or they have specified a restriction on IPv4 datagram length to maximum of 65,535 bytes. So in order to avoid this confusion, what they have done is they have kept a limit, so maximum restriction on the size of the payload to 65,535 bytes. So this is the maximum size specified. So uh, we have to divide the datagram to make it possible for it to pass through this network, and we call these process as fragmentation. As I said, so if the size is more than that of 65,535 bytes, we have to divide the datagram so that it can pass through the network, and the process of dividing this datagram into number of packets, we call it as, this process we call it as fragmentation. So when the fragmentation is done, each frame or the fragment has, or it will have, its own header, uh, with the most of the field repeated, and only some have changed. That is, whenever you divide a datagram into number of packets, so they will have their own header, but there is only few items, so the few fields will be changed, and most of the data will be same as the original datagram. Even a fragmented datagram can have, or maybe fragmented if come across a network with a smaller MTU. That is, once we fragment and when we transmit it again, there might be a cases wherein that particular network might require a smaller size in the fragment. So you will go for fragmenting the frame again. So first we have fragmented, that is fragmented again. So there is multiple level of fragmented. So the datagram might be fragmented before it reaches the final destination. So it means the tra- transmission path. So wherever it is required, so the packet will be fragmented. So fragmentation of datagram can be done by the host or any router in the path. So based on the requirement, either the source can be uh, so the source can the fragment the datagram, or in between the router, depending upon the uh, requirement of a network, even the router can fragment the datagram. However, when it comes to reassembling of this datagram, as I said, so when it undergoes a multiple level of fragmentation at the receiver, it is the only that particular destination has to take care of reassembling this packet. So when the packet is fragmented, payload must sorry the payload most part of the header with With some exception, option must be copied by the fragment. So when the packet is divided into a payload, header will be changed, and there is so most of the data will remain the same except few data. The host or the router that performs or that fragments a datagram must change the value of three different fields. Those three fields are flag, fragmentation offset, and total length. So whenever the fragmentation has been done, then there is a change in three fields. One is flag, second one is fragmentation offset, and the third one is the total length. As you have seen, in case of IPv4 datagram, there are three fields related to fragmentation. So one field is identification, second one flag, and the third one is fragmentation offsets. This identification is a 16-bit data which identifies the datagram originating from which source host. So this is going to identify, or this will have a data corresponding to the source host. So the combination of identification as well as the source IP address is a unique ID that is going to define a host, or that is going to define a datagram when it leaves the host. So it is a combination of identification bit as well as the source IP address. So when it combined together, there will be a unique ID, and that is going to define the address of the host. The second field is the flag, that is 3-bit flag. This is going to define the flags. So this, as I said, it is a 3-bit flag. You can see here there are 3-bit flag, first, second, and third. The first bit, the leftmost bit, is reserved. So whatever you can see in the black here, it is reserved. So it is not used. It has kept as reserve bit. The next bit, as you can see, it is D bit, which stands for do not fragment. So if it has a value 1, that is when the second flag bit is equal to 1, then the machine must not fragment. So if it cannot pass the datagram through any another available physical network, it has to discard the datagram and it has to send a error message. So if this bit is 1, that's D is equal to 1, that is do not fragment, then the machine or any router should not divide this datagram into further packets. So what will happen? So with the same size, the datagram has to pass through the available physical network. So there might be chances that so the data might reach successfully to the destination, or there might be a case wherein a particular router or network cannot carry this datagram. In that particular case, that network has to discard the datagram. So it is going to discard the datagram, and since it has discarded, it has to send a error message through ICMP to the source host. So an error message will be sent to source host saying that the packet has been dropped from the network. Next field is M. So before going to the bit M, so we'll see what is going to happen if the bit is 0. If the D bit is 0, that is D second bit is 0, then the datagram can be fragmented if necessary. So if there is a necessity of fragmenting the datagram, then we can do it depending upon the requirement. That is only possible only when that second bit D is 0, or else it has to be sent the data as it is. The last and the third bit that you can see here, that is bit M, which stands for more fragments. So if the value is 1 here, if that particular bit is equal to 1, it means the datagram is not the last of the fragment. That is, so whatever the data has been received, it is not the last fragment. There are few more fragments after this one. If this particular bit is 0, it means that this is the last or the only fragment. So it is a bit which indicates whether there is more fragments or not. If its value is 1, it indicates there are more fragments, and if it is 0, then it indicates this is the last or the only fragment related to the particular datagram. And the last one is a 13-bit fragmentation offset field, which shows the relative position of the fragment with respect to whole datagram. That is, since the original data is the datagram, with respect to this, what is the position of the fragment will be identified using this 13-bit fragmentation offset. You can see in this particular diagram, there is one datagram with size 4000 byte, that is from 0000 to 3999. So it is total 400 bytes. So this has been divided into three sub packets or three packet. So we call it as, this process we call it as fragmentation. So first fragment, second, and the third. So if you see this, the first fragment carries from 0 to 1399. So to calculate the offset address, what we do is we'll take the first data and we will divide it by 8. We divide it by 8 because the original datagram, whatever is there, that will be measured in terms of units, that is of 8 byte. So each datagram is measured in terms of 8 bytes. So we divide this particular first data by 8. So here the offset address will be 0000 divided by 8, that is 0. Let us take the second one, which starts from the next immediate, that is 1400 and goes up to 2799. To find the offset address, take the first address, the first number, that is 1400, divided by 8, so you get 175. So this is the offset corresponding to the second fragment. Similarly, for the third fragment, the starting number, it is 2800 and it goes up to 3999. So divide that first data, 2800 divided by 8, you are going to get it as 350. So this is the offset. So this is how we are going to calculate the offset of a fragmentation. So take the based on the number of fragment required, divide it into different number of fragments and divide the first data by 8, and you are going to get the offset address. The same problem or the same explanation has been given in terms of packets here. You can see you have a original data here that has been divided into three different fragments, that is f1, f2, and f3, and it is sent to the destination. So the original packet whatever was there, that has been divided into three, and as I said, it is a connection less oriented protocol. So there is a multiple path from the source to the destination, so they can go in this particular path or they might take this particular path. Since it is connectionless oriented, you can see here fragment f1 and f3 will move in this particular path, whereas here it is going to take the different path, that is f2 is going through a different path. Now you have a router here, and since it has been connected to one more router, that is one more network, so this particular router cannot handle this entire fragment f2. So what it is going to do is it is going to further divide this into f2.1 and f2.2. So entire thing will be once again fragmented at this particular router when sending the data in this particular route. So initially we had one that is divided into three at the source, and at this particular router the second fragment has been subdivided into two fragments. So once this is done, it will come to this particular router, and then it will come to this final router, and then to the destination. So you can see here while sending, first it has f1 has been sent, then f2, then f3. But if we look at the destination end, f1 has reached first, f3 has reached first. The reason because it has taken the shortest path, and later f2.1 and f2.2 has reached, but actual order is f1, f2 and f3. So at the destination, the network layer has to take the data, and it has to reassemble the data in the same order, and it has to give it to the upper layer. The same thing you can see explained using the offset address in this below diagram. We'll see it now. So you can see here the offset address initially it was 0000. As you can see here, the original packets starts with the sender, that is here. The fragments are reassembled at the receiver. So the value of the identification field is same in all the fragment. If you see the identification IDs, so this remain same in all the fragment as the value of the flags filled with the more bits set for all the fragment except the last. So except this last bits 000 175 350, this is the offset address. Rest all the datas are same. And when this packet, that is f2, is fragmented again, you can see the initial offset, that is 175. This has to be same, this is 175. There's a mistake here, even this has to be 175, but there is a change in this data. You can see here it is 820, this is 620. That is, once the packet is fragmented again from the second fragment, so the reference offset address will be same for the both, that is 175, 175 and 175. The only difference is this number, that is 820 and 620. So even if each fragment follows a different path and arrives out of order, the final destination, that is the final receiver, can still reassemble the original datagram from the fragment received using the following strategy. The first should be, the first fragment has an offset field value of 0. So initially you can see, initially the offset value will be 0. Divide the length of the first fragment by 8. The second fragment has offset value equal to that of result. Step 3, divide the total length of the field and divide the total length of the first and second fragment by 8. The third fragment has an offset value equal to that of result, and continue the process. The last fragment has its m bit equal to 0. Continue the process. The last fragment has more bit value equal to 0. So that is this case. See, more fragment 1, so m, here it is 0. So it has to verify at the receiver, it has to verify this m bit. So based on that, it can reassemble the data and send it to the upper layer. Hope you understood the fragmentation method and how the offset address will be calculated. Now we'll see few problem based on this. The first problem, it says a packet has arrived with an m bit value of 0, is this the first fragment, the last fragment, or the middle fragment? Do we know if the packet was fragmented? So this problem says a packet has come, and in that the value of bit is 0. What is m stands for? M stands for more fragments. So that we have seen now. So since the m bit is 0, it means that there is no more fragments, and the fragment is the last one. So whatever the data is arrived now, the packet has been arrived. So that is the last one since the value of m is 0. So the second part asked is whether it is a first fragment, last fragment, or the middle fragment. So since the value is 0, we can say it is a last fragment, but we cannot say if the original packet was fragmented one or not. Okay, so we can't tell whether it is a first or the middle fragment. Next problem, a packet has arrived with m bit value equal to 1. Is this a first fragment, last fragment, or a middle fragment? Do we know if the packet was fragmented? So in the previous problem, the value of m as given as 0. In this problem, it has been given as 1. So as I said, if the value of m is equal to 1, so it represents that there are still more fragments. So still more data or the packet has to come, but it might be one or more packet. So it is not the last packet. So solution is, since m bit is 1, it means that there is at least one more fragment. As I said, it might be one or more. But since the value is 1, so we can take it as one or more. This fragment can be the first one or the middle one, but not the least. So since the value is 1, so it might be the first, or it might be somewhere in the middle one. Since value is 1, so still one more to, or many more to come, so this is not the last one. So however, if we want to know whether it is the first one or the middle one, we need to have more information to answer the question. Moving on to the next problem, the problem says a packet has arrived with m bit value of 1 and fragmentation offset value of 0. Is this the first fragment, the last fragment, or the middle fragment? Um, since here it is given m bit is equal to 1 and fragmentation offset value is 0. Since m bit is equal to 1, so this might be the first fragment or the middle one. So, but not the last one, because since m is equal to 1, so still more fragment might will be there. Second one is fragmentation offset value is given as 0. So since it is 0, so it is a first fragment. So since here two condition has been given, based on both the condition, m bit is equal to 1 and fragment offset value is given as 0, so it is the first fragment. Next one, a packet has arrived in which the offset value is 100. What is the number of first byte? What is the number of the first byte? Do we know the number of the last byte? So a packet has arrived which has got a offset value of 100. So what is the first byte, and we have to calculate the number of last byte in the from the given offset value. So, to calculate the number of first byte, what we need to do is we have to multiply the offset number by 8. You remember we have divided to calculate the offset number by 8 there. Same way, to get the number of first byte, we have to multiply the offset value by 8. So, the offset value is given as 100. So, multiplied by 8, which gives us 800. So, this means that the first byte number is 800. The second question asked is, uh, do we know the number of the last byte? So we need to calculate the number of the last byte. But since the length of the data is not given, so we cannot calculate the number of the last byte. So in order to calculate the last byte, we need to have the length of the data. We'll go with the last problem related to this particular topic. Problem says a packet has arrived in which the offset value is 100, the value of HLEN is 5, and the value of total length filled is 100. What is the number of first byte and the last byte? So according to this problem, a packet has arrived which has got a offset value of 100, and in this problem the HLEN is given as 5, that is the length of the header is given as 5, and the total length filled is given as 100. Using these three data, we need to calculate what are the numbers of the first byte and the last byte. Let us calculate the first byte first. So given offset value is 100, we know we have to multiply it by 8 in order to get the first byte number. So 100 multiplied by 8, which will give 800. So the first byte number is 800. Now we'll calculate. So given that total length is 100 byte and header length is given as 5. So since we know that field is 4, we have to multiply it by 4. So header length we get it as 20 bytes. So which means there are 80 bytes in the datagram. That is, so 20 into 4, so 80 bytes in the datagram. So if the first bit number is 800, so that we already calculated, the last one should be, so 800 plus 80, so total it will be 879. So the last byte number will be equal to 879. So with this, we'll move on to the next topic, which deals with option fields and security related to IPv4.